Yeah.
Okay. Thank you very much. Good afternoon, everybody. As Daryl said, my name is Younes Manton. I work at IBM in the Runtime Technologies group. I focus mostly on compilers, and today I am here to talk to you about JIT Compilation and service. So if you were here at last year's workshop, you probably heard a talk on the same topic. That was given by a team member of ours where he introduced the project for the first time. I'm going to cover most of the same information just so that everybody is up to speed and we're all on the same page. And then I will tell you about what we've done in the last year, what we've learned, and what that might mean for runtime development. So let's start off by first talking about JIT compilation in general. So if you are a runtime developer or a Java developer, runtime enthusiast, you probably know that Java applications tend to start off very slowly. They ramp up over a period of time, and eventually they hit peak performance. You know that if you've ever profiled a Java application with the right tools and at the right time, you probably noticed that it probably takes up a lot of CPU time, the JIT compiler, and it takes up a lot of memory to do what it does. So in that sense, it actually competes for resources with your application. So the underlying assumption here that we make is that eventually you break even on the resources that the JIT compiler used. JIT compiler produces optimized code, and eventually if your application runs long enough, you hope to break even and you hope to get more performance than what you put into it. And typically that has been true in the past. It's been true when people used to develop large monolithic applications that ran for a very long time. But we're finding that it's less true nowadays. Nowadays people are developing smaller applications, microservices style applications. They're spreading them out over multiple processes. They are starting them and stopping them on demand, and they may only run for a very brief period of time. So we, as JIT compiler developers, needed to find a compilation model that better fit this environment and was better able to cope with these sorts of constraints. So let me throw out some what ifs. What if the compiler didn't actually have to compete with the application? What if the compiler could run elsewhere, say on a separate machine? What if we could use multiple compilers and a cluster of machines? What if all of those compilers could compile code for all of our applications simultaneously and actually share the results? That's essentially the idea behind JIT as a service. It's a way to decouple the compiler from the rest of the JVM and have it operate independently as quote-unquote a service. And that way we can, the application doesn't have to know what kind of compiler it's dealing with. It doesn't have to know how many threads the compiler is consuming. It doesn't have to know how many compilers it's dealing with. It doesn't have to know if the method that was compiled for it specifically or for another application maybe 5 minutes ago or 5 hours ago. That's essentially the idea here, is to be able to separate the two and to be able to do more intelligent things with the compiler once they're separated. So what we're really describing, in essence, is a way to expose compilation to the cloud. We want to treat compilation just like any other service in a service-oriented architecture. We want to be able to do intelligent things with it when it's a service. We want to be able to decide independently of the application how many CPUs and how much CPU resource we want to put into it, how much memory we want to allocate to it. We want to be able to ramp that up and down independent of the application as necessary. We want to be able to take advantage of redundancy and essentially to be able to amortize the cost of compilation across processes and applications. And because JIT as a service runs over the network, we can containerize it, we can manage it more intelligently. You can use something like a Kubernetes or an IBM Cloud Private or an OpenShift or what have you to control it and treat it just like any other component in your architecture and to be able to do smarter things with it. So the benefits of this are quite obvious, I think. For the most part, they speak for themselves. You have explicit control over the compiler. You are able to decide on the resources that it gets, and you're able to manage it more intelligently. You can scale it up and down, like I mentioned, and you can amortize the cost. So that last point is actually very important. You can imagine in a cloud deployment, your application is spread out over multiple processes, and in a traditional JVM, each one of those processes is going to have a JIT compiler. That JIT compiler is probably going to be compiling the same code over and over and over again. You're going to have to pay the price across all of your processes. With JIT as a service, once we've extracted the compiler from the picture, that code only has to be compiled once. You only pay the cost of compilation one time across all of your applications. So you can imagine that if you have an application spread over multiple processes or multiple applications, you only have to compile the Java class library effectively just once. And the cost of that goes down relative to the number of applications that you deployed. So it's one thing to be able to tune the JVM for a cloud environment. The OpenJ9 JVM actually does that relatively well, but it's another thing entirely to break the JVM up into components and to have it run in the cloud in a more intelligent way, similar to the rest of your application. I hope I've stressed that point enough. I feel like I've repeated it a few times. So let's talk a little bit about the project itself. This project started early last year. I mentioned that we presented it for the first time at last year's workshop. And at that time, we didn't actually even have a fully working prototype. It was a nearly working prototype that could run some applications. It ran partially over the network in that the client and the server communicated for the most part over the network, but the compiled code that the compiler produced was actually shared with the client via shared memory, via a file on disk that's memory mapped. If you are familiar with OpenJ9 and the IBM JDK and shared classes and AOT functionality, this was essentially piggybacking off of that effort to try to get it up and running quickly. At the time, as I said, the compiler wasn't at a point where it could run an application. It didn't do any optimization at all at the time, and it was a very basic implementation at last year's workshop. So the problems that we started to tackle at that time were really had to do with the way our code base was structured. The compiler has always been an in-process compiler, and all of that had to change once we moved it out of process and across the network. So a lot of the early effort was spent thinking about how the interface between the compiler and the rest of the JVM and the application would look like, how we would structure things, how things would work over the network, how we would handle things like resiliency and network traffic, and servers going away and coming back, and clients having to deal with that. So we first started by forking OpenJ9 itself. We worked on Linux x86, and we started to implement the networking layer using gRPC, which is an open source remote procedure call framework, and protocol buffers, which gRPC uses under the hood, which is a serialization framework to get a basic networking infrastructure up and running. and then we built up from there. So the initial prototype, for the most part, as I said, communicated over the network, but still had this shared memory component. So it wasn't able to run on separate machines at that time. From then, we just added more functionality and slowly built up over time. So where are we today? First and foremost, I am happy to tell you that all of this code is open source. You can find it at the OpenJ9 project alongside the rest of the OpenJ9 source code. It's in a separate branch at the moment. I will give you a link at the end of the presentation to that. But it is all open source. The server-side JIT supports nearly all of the optimizations that the conventional JIT does. The entire compilation process actually works over the network. It can fall back to doing local compilation if necessary, if the server drops out for any reason. And this is actually something that we've been experimenting with, mixing local compilation with remote compilation to try to mitigate networking, latency, and things like that. So if you see a talk in next year's CastCon about how to intelligently schedule compilations in the cloud or something along that nature, don't be surprised. The current implementation actually no longer uses gRPC. So once we started tackling some of the bigger bottlenecks, we found that eventually gRPC itself became a bottleneck. And the reason for that is largely because gRPC works by communicating over HTTP. So all of the requests and responses are wrapped in an HTTP request and a response. That's essentially a lot of text processing that has to be done. Requests have to be built up, headers have to be built up. Server has to parse that and repeat the process, and the client has to also parse that. So essentially, we found that as we went along and got rid of a lot of the other bottlenecks, that became its own bottleneck. So we eventually moved on to dropping gRPC and manipulating sockets ourselves, along with protocol buffers, and that actually had a significant impact on CPU utilization. The server JIT can actually handle multiple clients at any given moment, although it's important to mention that at this very moment, we don't actually share code between clients. I'll come back to that a little bit later on, but that's an important distinction to make, just so we're all on the same page. There is support for encryption using OpenSSL. So this guards against essentially man-in-the-middle attacks. We have that option of using encryption. And finally, we can more or less run the entire OpenJ9 test suite. We can run a fair number of applications, including enterprise applications, things like WebSphere, DayTrader, the DayTrader benchmark, the Acme Air benchmark, and so on. Okay. So by now you're probably wondering how this thing actually works. And the short answer to that is it actually works pretty much like any other client-server application. It turns out that compilation, especially asynchronous background compilation, is actually at a very high level, very easy to make into a network, into a client-server model. So essentially, the client initiates communication with the server, sends a request to compile some code, carries on with the application, and eventually receives a response from the server with some compiled code. So conceptually, it actually fits very well with just about any other sort of client-server model. Thankfully for us, Java bytecode was designed to be compact. It's relatively easy to send over the network, and compiled code is also fairly compact and easy to send back. So all in all, it actually works in a fairly straightforward manner. So let's dig in to the details just a little bit. Okay. So here we have a basic flowchart of how both the client and the server work. Step one is that the application starts running in the interpreter, just like it normally would. And as the interpreter is executing bytecode, it's calling methods. As it's calling methods, it's also querying the JIT compiler. So it's going to be asking the JIT compiler, do you have a compiled version of this method that's about to be called? If the JIT compiler responds yes, then the interpreter jumps to the compiled code. If not, the interpreter just keeps interpreting. On the flip side of that, the JIT compiler actually keeps track of what's being called, and it takes some decisions about what to compile and what not to compile. So once the JIT compiler decides to compile something, it essentially ends up on a queue. So that's step two. Step two is that we have multiple compilation threads working in the background, and they are essentially popping requests off that queue and looking to start the compilation process. So this is where we actually diverge a little bit from the conventional JIT. In the conventional JIT, the compilation thread will pop that request off the queue and carry out the entire compilation process from beginning. So parse the Java bytecode, it will generate an internal representation, it will generate machine code, and basically install that. For JIT as a service, this is the point where we actually communicate to a server. So a compilation thread will initiate a connection to the server and pass the request along. It will pass along the Java bytecode and along with some metadata that the server needs to start the compilation process. And this is step three. The server works very similarly to the client. It also has a queue. So once it receives compilation requests, it puts them onto a queue. That's step four. And it also has multiple compilation threads on the server side. So that's step five. Each compilation thread on the server side is going to pop a method off of the queue and begin the compilation process. So as each thread goes through the compilation process, it's going to periodically have to call back to the client. This is in order to get information on the state of the program, essentially. So, for example, the state of the class hierarchy at the time, any sort of profiling information, for example, the number of targets for a particular virtual call, distribution, and things like that. So it's going to call back to the client to get that information. It's going to carry out the compilation process. And eventually, it's going to emit some machine code. That's step seven. And it's going to send that machine code back to the client compilation thread. Client compilation thread is going to perform something we call relocation, which is essentially taking that machine code, installing it at a particular address, and fixing up the instructions so that the code is actually runnable. And that's the entire compilation process from beginning to end, from client to server and back to client. Okay, so now we're going to talk some numbers and see what performance and resource utilization looks like in this environment. Okay, so here we have a graph of throughput. This is a Java web application benchmark called Acme Air. And the essential point in this graph is that you can see that OpenJ9 with a conventional JIT and OpenJ9 with a JIT as a service variation of the JIT essentially reach roughly the same peak throughput. You can see that there's a little bit of a difference there, a little bit of a delta, and that is owing mostly to the fact that we haven't implemented every single optimization that the conventional JIT does. Also, this is just, we've implemented all of the low-hanging fruit, all of the big hitters, but there's a few odds and ends left. And then the other thing is that the JIT as a service compiler isn't quite as aggressive as the conventional compiler. So essentially it doesn't try as hard. And that's due to tuning and heuristics and things that we have to adjust on the server side once we are completely functional, and it becomes apparent that we should investigate that and put some effort into that. The other thing you will notice is that the JIT as a service graph is actually shifted a little bit to the right, and that's actually a more interesting point to me, and that's the effect of latency. That's essentially the effect of latency in aggregate. So everything that happens in the conventional JIT happens when you deploy the JIT network. It just happens a little bit later, and you can kind of see that ramp up is shifted to the right a little bit, but it looks roughly the same, and peak throughput. We move on to the next slide. Actually, I'll add a little bit. Takeaways. So the takeaways I just mentioned are that we don't actually have to sacrifice peak performance. There is nothing inherently different about doing compilation over a network and doing it. You can essentially produce the same code more or less. There's no downside or an inherent disadvantage. And two, that network latency is actually tolerable, especially when you look at it in aggregate. So I'll talk a little bit about the per method latency a little bit later, but the important point is that when you look at it in aggregate, it really doesn't contribute all that much. I'll talk a little bit about that shortly. So if we move on to the next slide, here we have a graph of memory consumption. This is essentially graphing resident set size for both OpenJ9 with conventional JIT and JIT service. And what we can see here is that the conventional JIT tends to a lot more memory near the beginning of the program. And this actually makes sense because JIT compilers tend to use most of their memory and allocate most of their memory when they're actually doing compilation. So a JIT compiler will allocate some persistent memory that lasts throughout the entire life of the process. But it's actually very minimal. Most of the memory that's consumed happens as it's doing compilation, and most of the compilation naturally happens when the program starts and nothing is compiled. So here we can see that peak memory usage is somewhere in the 325 megabyte range for the conventional JIT. Then it starts to tail off once everything is compiled, and you essentially have a graph of the application's memory usage after that. Compare that to the JIT as a service client. We can see that there is no spike in memory usage. All of the compilation is happening elsewhere, and the graph essentially looks more or less like the application's memory usage. It's important to note that this is graphing memory usage on the client side. So for JIT as a service, there is a server somewhere else running the compiler, and it's obviously using memory. So there is no free lunch here. We didn't manage to cut memory usage by hundreds of megabytes. We've essentially shifted it. So the takeaways here are that when you use JIT as a service, the application's memory usage becomes the dominant factor. So if you are sizing your containers and your machines to run a particular application, you don't have to care about what the JIT compiler is doing. You size it for the application. Size your container for the application, and size the machine for the number of containers and applications you expect to run, and you don't have to care about the peak memory requirements of JIT compiler, which are actually very hard to estimate unless you actually know what you're doing and you know a little bit about the implementation. It's much more straightforward. Okay. Finally, we'll get to a chart of the most interesting scenario. This is throughput in a very constrained container. This container has 64 megabytes of memory available to it and half of a CPU. And essentially, we can see that OpenJ9 or the conventional JIT manages a very flat throughput. It doesn't have any ramp up at all. It's barely doing anything. Compare that to the JIT as a service JVM, which actually does manage to do a significant amount of work. It manages to reach a significant amount of throughput, and you can actually see some spikes in the performance, and that is due to garbage collection kicking in every once in a while. But by and large, this configuration, JIT as a service JVM, actually does manage to do some work. And we've also charted hotspots here just to make it clear that it isn't anything that the OpenJ9 JIT is doing. It's not resource constrained or resource hungry in any way. It's hotspot JIT, which essentially works roughly the same way, is behaving very similarly. As far as the OpenJ9 conventional JIT goes, it's actually throttled itself down because it sees that we don't have very much memory, and it's doing the bare minimum amount of work. So it's being very conservative in its compilation, doing fewer compilations, doing less aggressive optimization because it's trying not to max out the little bit of memory that we have. Hotspot, I have no idea what it's doing, but the takeaway point is that it can't manage throughput either. Whereas if you move compilation to another machine, you can actually manage to get some work done on the application. So basically, the takeaway is that you can actually run Java in a very constrained environment if you move the compiler. And the reason that becomes important is because you can actually run many, many applications on a single machine. You can move the compiler to a separate machine. You can bring that machine up when it's required and ramp it down when it's no longer required. So it becomes possible to scale in density, so you can run a tremendous amount of Java applications on a single machine and bring the compiler up and down as necessary, and it actually manages to do work. And finally, I'll leave you with miscellaneous statistics. On average, the remote JIT as a service uses about 77% less CPU time versus the conventional JIT. But I have to remind everybody that that's not exactly an apples to apples comparison. As I mentioned, the JIT as a service JIT isn't quite as aggressive as the conventional JIT. It doesn't do all of the same optimizations, but if you're just going to measure it, you get a 77% CPU utilization savings. If we were to do a more apples-to-apples comparison, if we had the conventional JIT and the JIT as a service JIT do roughly the same amount of work and the same number of optimizations, you can measure about a 40%, nearly 40% CPU utilization savings. And the time to compile per method in the JIT as a service case is actually 2 to 4 times more. So I promised I'd come back to that earlier, and 2 to 4 times actually sounds very bad. I'll be honest with you, I was very skeptical about this project when it first started. I've worked in JIT compilers for a long time, and I've seen the effects of ramp up and the JIT having to do work for short-running applications and for applications that manage to find the worst possible behavior in this sort of thing. So I was a little bit skeptical about what adding network latency to the equation was going to do. But as we saw in the earlier graph, it doesn't really matter what the per compilation latency is. It matters what the aggregate effective latency is. We have multiple compilation threads. They're able to overlap work, and what you can do is effectively hide latency. So I didn't believe it until I saw that earlier graph with a very slight shift in throughput. So I think I'm more of a believer now. I think that while we can optimize current method latency by actually trying to reduce that and trying to reduce communication back and forth between the client and the server. We can also optimize it by just simply doing more work and scaling the number of compilations we do and effectively hiding network latency. Okay. So now we'll talk a little bit about future work, where we hope to be in the future. Biggest item on the horizon is actually being able to share compiled code between clients. I mentioned earlier that we don't currently do that, but that's really the next big step in exploring this compilation model, is to be able to share code between clients, to be able to amortize the cost of compilation, as I mentioned, and to be able to realize the potential that we have here. After that, I mentioned we still have a few optimizations to tackle, a few odds and ends and things that, in the grand scheme of things, aren't that important. The last remaining items we have to tackle. We want to also be able to experiment with mixing local and remote compilations, being able to intelligently schedule compilations, being able to do a local compilation on the client if and when it seems like it will be very useful to do. I still don't know what that scenario will look like, but that's something we hope to explore in the next 12 months or so. And finally, we hope to be able to merge this code back into the OpenJ9 master branch, so that if you happen to find yourself with an OpenJ9 binary, you can actually try it. In the meantime, you can build it from source. It's fairly straightforward. If you've ever built OpenJ9, there's really not that much more to it. As far as where to find it, these are some links to the actual repositories. There is a JIT AAS branch on the OpenJ9 Git repo. There's a corresponding JIT AAS branch on the OpenJ9 version of OMR. And finally, you can always find us on Slack. And finally, if you want to see a live demo of all this, Mark Stubley gave a great demonstration last week at one under a very bright set of lights. Did a wonderful job. You can check that presentation out. I tried to find a still frame that was very generous. I hope I succeeded. And with that, thank you very much for listening. I'd be happy to take any questions.
I guess maybe this question might not be directed well, but as you said during your talk that you were very skeptical of JIT as a service when you started this. But you also mentioned that it moved a lot of things that were being done. It allowed you to have smaller containers. It allowed you to move some of this work that's being done concurrently to another node on the cluster, right?
Right.
So have you thought of, or has anyone else thought of, maybe taking one of the more parallelizable concurrent garbage collectors and doing the same thing? Try to make one kind of node or a number of nodes on the network that do all of the big heavy lifting administrative tasks of the JVM that are not part of running the application and do it over the network.
Okay, so if I could summarize your question for the recording, I think the gist of it is that we've moved compilation over to another machine out of process. Can we do that for garbage collection and some of the other things? And I did think of that this morning. Actually, I anticipated somebody might have that sort of question. And, I couldn't wrap my head around doing garbage collection out of process, because the garbage collector is essentially moving memory around in process. So it wasn't immediately clear to me how that could be done feasibly. You might be able to use RDMA or something like that, but it wasn't clear to me that garbage collection could be done. And as far as some of the other things that the JVM does in the background, to be honest with you, I can't think of anything that's as heavy as compilation. Compilation is like at the top of the tree, and there really wasn't anything else that I could come up with to answer that question I was expecting. But it's certainly possible that you can move other things. I don't know. Hope maybe somebody with a lot of imagination will lead this talk today and think of something I don't know, but it wasn't immediately clear to me.
Yeah, I had quite similar question. I was actually wondering if you are doing some more sophisticated, like offline metadata processing in order to, I don't know, like improve profiling.
Okay. So the follow-on question was if there was any sort of processing of metadata and profiling data that we could move process. And actually, we have thoughts along those lines. So if you have a JIT compiler that's running as a service, servicing multiple clients, they may be running the same application or a mix of applications. It's possible that you can do some more sophisticated analysis, looking for patterns, compiling code. Let's say you figure out that a certain group of applications or processes is running code in a certain way, and the profiling data from this group looks a certain way. You can compile code specifically for those guys, and another group may have a different profile. They may be executing code in a completely different way, and you can compile code for them. So, for example, Java lang string, you may compile it one way for a group of applications that are processing English, and another group of applications that are processing Japanese or some other language. The actual behavior of some of the string conversion routines and things like that is going to behave differently. There's potential there to optimize differently for different people. If you have all of that information in a server, if that server has enough CPU time to do what it wants, and it doesn't have to be conservative.
I think one of the more interesting areas there is that when you move the JIT out of process onto a separate machine, that can change some of the trade-offs for what kinds of profiling you can afford to do, right? So when you're a JIT inside a JVM and you need to profile what's going on in that JVM, you're relatively constrained because you can't afford to impact the runtime performance of that JVM much.
Yeah.
But you're connected to 10 JVMs that are all running roughly the same workload. You can collect more rich profile data by spreading out the overhead across those 10 JVMs, and then maybe collect more rich profile data with which you could then further optimize the program. And because you're in a separate place, you can afford to do much more strenuous analysis using that richer profile data. So I think we haven't gone down this road yet because we're still kind of finishing off the plumbing, I guess. But going forward, I think it offers some very interesting opportunities for employing a lot more strenuous optimizations and collecting much more rich profile data than we've ever been able to in a dynamic environment. So, pretty cool.
Yeah, you have already proved as presentation was saying that you already are collecting it, so it's just processing.
We are collecting profile data for sure. We need to do that in order to compete with the in-process JIT, right? You can't get that level of performance without collecting profile data about the application. What I'm saying is we haven't started doing anything more than that, but I think the opportunity is there to be.
Partially answered my question. I was going to ask, I think I thought I heard you say earlier in the presentation that you're not compiling as aggressively JIT as a service as JIT. And now you have all these rich profile data, you have sources in the JIT as a service process, resources. So I just wondered why you're aggressive
just to repeat the question, it was essentially, why are we not compiling as aggressively JIT as a service version of the JIT versus the conventional JIT? That really just comes down to the heuristics that we have in place and disabling some of the higher end optimizations allowed the implementation to go, the work essentially to go faster. We didn't have to tackle some of the thornier issues. Essentially, those higher level optimizations, as you can see from the throughput graph, don't contribute that much to throughput in the end, but implementation-wise are a little bit harder. So one thing that I can think of off the top of my head is something we call the known object table, which essentially has the compiler examining objects that are live in the program so that it can optimize them. That's very difficult to do over the network. Right? We still haven't quite gotten to that point, and it really wasn't clear that it was worth the effort at that point. It's just more of a trade-off of the amount of work we need to do that versus payoff.
So has any thought been put into maybe logging the data that's being sent from the client to the JIT service server in order to reproduce problematic compilations?
By me personally, very little, but in a more general answer is that yes, we have looked at this sort of problem in the past of reproducing compilation. We don't do any logging in our code base to do this, but we have thought of that. Another similar thing that we've thought about in the past is reproducing compilations from core files. By moving the JIT compiler out of process, the front end doesn't actually have to be a Java application anymore. It could be a core file, some program that's reading a core file and punting requests over to the server, answering the server's queries for the state of the class hierarchy and profiling information by fetching it out of the core file and feeding it along. So the short answer is yes, we've thought about it. I haven't thought about it much myself, and we don't do that yet. It's possible, and maybe on the horizon.
Okay. All right. Thank you, Younes.